Well, we're back at the science cave this morning. Uh, as you can probably tell, I don't have a life. It's like 8 o'clock on Saturday morning, but well, let's go on with it. A couple ideas on the test I see a couple people struggled with. One was humidity and temperature. Humidity, humidity and temperature. From the class discussion and from the video we had with the sandwich bag and the garbage bag, we know that warmer air holds more water moisture or water vapor, if you will, than cold air. Cold air has greater density, the particles are closer together, therefore, the little water molecules can't fit in there as easily. Warm air, on the other hand, moves around more. There's more space between them, so you can get more little water molecules stuck in between them. So, if we kept the amount of water vapor constant, the relative humidity or that ratio at warmer temperatures got to decrease. Now I didn't do the math in class, and maybe I should, but when you talk about relative humidity or RH, when you talk about that, it's really the air's actual water vapor content. So we'll just put down actual H2O content because we're looking at a ratio here all over what it has to have to be saturated. So we can say H2O for saturation. Saturation. This the amount of water vapor you need for saturation, it's a big long formula. You can calculate it, but there are some definite values at different temperatures, and we're going to go and just do a couple of these and mathematically show why the relative humidity will go down with temperature. So let me flip this off here. All right, let's just say, for instance, so we've got, and I'll put the units in, we got 2 grams of water vapor, 2 grams of H2O per 1 kilogram of air. 1 kilogram of air. That's that's how much is there. That's how much is in the air right now. We've got 2 grams of water vapor for every 1 kilogram of air. Well, at 0 degrees, and I'm just going to do a couple of these, at 0 degrees, for saturation to occur, or 100% relative humidity, you need 3.5 grams per kilogram. So the value here is 3.5 grams per kilogram. Well, relative humidity really is the ratio of this divided by that. So we can do the ratio here real quick. And we got 2 over 3.5, and if it's a ratio, it's in percent, multiply by 100, and that's going to equal about 57%. So at 0 degrees Celsius, with this much water vapor in the air, the relative humidity would be 57%. Well, let's kick it up to 15 degrees Celsius. At 15 degrees Celsius, the amount of water vapor in the air for saturation is 10 grams. And again, if you want to do, I can give you a nice long formula if you want it. You can. This is the value that is given. So we can do the math again. Remember, we are holding this amount up here. We are holding it constant. That stays the same. So now we've got 2 divided by 10 times 100. And I think if my math is right, that is about 20%. Well, as you can see, we dropped pretty significantly between 0 degrees Celsius and 15 degrees Celsius. The temperature is going up, and that's that whole idea there. The next thing I'd like to go over real quick again, let's do another, we'll do another mountain problem here, the adiabatic lapse rate. Open this one up, and let's see if I can, let's do another adiabatic lapse rate problem here. And let's say we've got our mountain. And let's say we're on the windward side. This would be the windward side. We'll just say we're at sea level. We're at 0 meters. We're at 0 meters here. And the temperature on the windward side, temperature is 20 degrees Celsius. And the dew point is determined to be 0 degrees Celsius. Alright. And we want to know what the temperature is on the leeward side. And again, the leeward side of the mountains are going to be dry. It's typically the rain shadow area. So we know we've got a couple different rates. The dry rate, dry adiabatic rate, is 10 degrees per 1,000 meters. And we know the wet adiabatic lapse rate, if you will, is 5 degrees per 1,000 meters. Well, we can kind of figure, and I guess I better put this in. I don't think I told you. Let's say the top of the mountain is 3,000 meters. Alright, and we want to know what the temperature is over here. Well, we know if we go up to the 1,000-meter mark, we're going to drop 10 degrees. So it looks like we're 10 degrees right here. We have not hit the dew point yet. So it looks like we've got to go up. Let's go up another 1,000. And so we're at the 2,000-meter mark. And we're going to drop another 10 degrees. And we end up at 0, which is the dew point. In fact, you can probably tell at 0 we'll probably have snow here. And in fact, many times you're out in the mountains, you'll see snow at the upper elevations, but you won't see it at the lower. And this is the reason why. We know as you increase in altitude, temperature goes down. You got to get to that dew point. So we go up another 1,000. We're only going to drop at the wet rate. And so from 0 for drop in temperature, it's going to be at -5 degrees. Well, let's see what it is on the leeward side. So we go down the mountain. We're at the 2,000-meter point. We always warm at the dry rate. Moisture is all pretty much all squeezed out at this point. So -5, we'd go to a +5 degrees Celsius. Let's drop another 1,000 meters. That takes us to 15 degrees Celsius. And if we go back down to our beginning, lo and behold, we're going to be at 25 degrees Celsius. So we warmed up 5 degrees on this one. Again, as you go, as you do these problems, you can extrapolate any values you want in here. If the dew point was -3, for it's 1 degree for every 100, you could extrapolate that. Or if the dew point was 5, whatever it would happen to be, you can extrapolate those values. So if you got any questions, for you guys retaking the test, feel free to ask, and I'll get this posted, and have a good weekend.